All right, welcome to this explainer. Today we're going to look at the hidden mathematical rules that power, well, basically everything in our universe. We're talking everything from ancient historical puzzles all the way up to the modern video games you play every day. Have you ever wondered why certain numbers behave the way they do, or how computers actually manage to keep your digital secrets safe? The answers to all of that lie in a fascinating field of mathematics that honestly sometimes feels like pure magic. Okay, let's dive into this with a quote from the renowned German mathematician Carl Friedrich Gauss. He once boldly declared, "Mathematics is the queen of the sciences, and number theory is the queen of mathematics." Just think about that for a second. In the massively expansive world of math, with all of its complex geometry and algebra, number theory is considered the absolute royalty. But what exactly is it? And why in the world did Gauss hold it in such incredibly high regard? Simply put, number theory is the study of integers. Those are your positive and negative whole numbers, like 1, 2, 3, and so on. It looks at their hidden relationships, their properties, and their patterns. Now, unlike the kind of math you might use to, say, calculate the speed of a moving train or figure out the area of a circle, number theory moves completely beyond continuous change. Instead, it focuses purely on the fundamental, discrete behavior of whole numbers. It asks questions like, how do these integers divide, multiply, and relate to one another behind the scenes? It's kind of like a giant puzzle. So here's our roadmap for the explainer today. 1. The queen of mathematics. 2. The integer building blocks. 3. Primes, atoms of math. 4. Hidden patterns and puzzles. And finally 5. Real-world digital magic. Let's start with section 1. The queen of mathematics. The absolutely crucial point I want you to take away here is this. Studying number theory isn't just about memorizing a bunch of boring formulas. It's actively building your core logical framework. When you study the behavior of integers, you're developing high-level logical reasoning, abstract thinking, and proof skills. You learn how to spot a pattern, rigorously prove exactly why it works, and then apply that knowledge to solve far bigger problems. These are the exact abilities that are essential for future success in literally any STEM field, whether you're aiming to be a software engineer, a computer scientist, or even an astrophysicist. Moving right along to section 2, the integer building blocks. Look, we all know the basic difference between odd numbers, which aren't evenly divisible by 2, and even numbers, which are. But in formal mathematics, this simple classification is known as parity. Understanding parity shows us how math is a highly logical, structured system. It's not just about counting things, it's a remarkably powerful tool for logical deduction. In fact, you can actually treat these parity rules like a literal, secret cheat code. An odd number plus an odd number always equals an even number. Just look at 3 plus 5. Boom, it equals 8. And an odd number multiplied by an even number, that will always, for sure, give you an even number. So why does this matter for you? Because by applying these parity cheat codes, you can instantly verify really complex algebraic equations, or quickly eliminate incorrect multiple choice answers on a test, all without having to do the grueling full mathematical calculation. It's a total game changer. And this brilliantly illustrates the difference between factors and multiples. Think of factors as the exact building blocks that divide a number evenly, leaving absolutely no remainder. For example, the factors of 12 are 1, 2, 3, 4, 6, and 12. Multiples, on the other hand, are what you get when you multiply an integer by another whole number. So the multiples of 5 are 5, 10, 15, and so on. Oh, and here's a really fun fact for you. Every single number is both a factor and a multiple of itself. And the number 1? Well, it happens to be a factor of every single whole number in existence. Let's jump into section 3, primes, atoms of math. Let's contrast prime numbers and composite numbers because this is where things get really cool. A prime number is an integer strictly greater than 1 that can only be divided evenly by 1 and itself. Think of numbers like 2, 3, 5, 7, and 11. They are completely unbreakable. You just cannot split them into smaller integer chunks. Composite numbers, on the other hand, like 4, 6, or 8, have more than 2 distinct divisors. This means they are literally composed of those prime building blocks. Basically, every single composite number in the universe is just a combination of prime atoms smashed together. Now, consider a really punchy, mind-bending fact about the number 2. Out of all the infinite even numbers stretching out into eternity, 2 is the absolutely only even prime number in existence. No way, right? Every other even number can be divided by 2, making them composite. But 2, it stands entirely alone. And here is another surprising math fact. Look at the number 1. You might intuitively think it's a prime number, right? Actually, scratch that. In modern mathematics, the number 1 is considered neither a prime number nor a composite number. It sits in a completely unique category of its own purely because it only has a single positive divisor, itself. It just doesn't fit the rule for primes, which require exactly 2 distinct divisors. All right, moving to section 4, hidden patterns and puzzles. So you very likely studied the Pythagorean theorem, a squared plus b squared equals c squared. Usually it feels like just a rigid geometry rule for measuring right triangles, but finding perfectly whole integers that fit this equation is actually a classic number theory puzzle. The sets 3, 4, 5 and 5, 12, 13 fit it perfectly. It proves that beautiful, perfectly clean integer relationships are secretly hiding right there inside the sharp angles of geometry. Now, what's really interesting about this slide is how Fermat's last theorem takes that exact same concept we just talked about and totally breaks it. Way back in the 17th century, a mathematician named Pierre de Fermat proposed that if you change the exponent from a 2, like we saw in the Pythagorean theorem, to anything greater than 2, suddenly no perfectly whole integer solutions exist anymore. None. Zero. It looks like a seemingly simple integer puzzle, yet it completely stumped the entire world. To give you a real idea of just how complex number theory can be, Fermat literally jotted this theorem down in the margins of a book in the 17th century. And it wasn't until the 1990s, an astonishing 358 years later, that a mathematician named Andrew Wiles finally proved it. Think about that. For over 3 centuries, the brightest minds on the planet tried and failed to solve what looked like a basic algebraic equation. That right there is the challenging, captivating beauty of number theory. And finally, section 5, real-world digital magic. You might be wondering, what does this all mean for us today? Well, these pure, ancient math concepts are actually the absolute foundation of our modern digital world. If you love computer science, coding, or video games, number theory is quite literally your secret language. Why? Because computers process absolutely everything in discrete, whole numbers, specifically zeros and ones. The lightning-fast algorithms that run your favorite video games, and even the equal temperament dividing up the musical scales in the songs you listen to, all rely heavily on the hidden rules of integers. But wait, it gets even more incredible when it comes to modern security, public key cryptography, banking security, e-commerce websites, and error-correcting codes all completely rely on number theory. Remember those prime numbers we called the atoms of math? Because it is so incredibly difficult to figure out the prime factors of massively large numbers, prime numbers are the direct foundation for the algorithms that keep your passwords, your bank accounts, and the entire internet secure today. Literally, without prime numbers, the digital world would be completely defenseless. Which brings us to our final point, and a massive opportunity for you. Despite powering our entire modern world, number theory is still full of unsolved mysteries. Conjectures like Goldbach's conjecture, which guesses that every even whole number greater than 2 is the sum of 2 primes, or the incredibly famous Riemann hypothesis regarding the distribution of primes, remain totally unsolved to this day. They're basically the modern-day equivalents of Fermat's last theorem. So I want to leave you with this provocative thought. By mastering these integer building blocks today, will you be the one to finally solve them tomorrow? Thank you so much for joining me for this explainer, and keep looking for those hidden patterns all around you.